Hello everyone, myself Nisha Bharti. In this session, I am going to present the presentation on diversity techniques. First of all, we will see what are the challenges in wireless communication. These are high data rate, seamless and high mobility requirements, spectral efficiency challenge that is 2 to 10 beats per second per hertz, frequency selectivity due to large bandwidth requirements, seamless coverage and support across different networks, devices and media forms, reliable communications, harsh wireless channel, scarce radio spectrum and energy constraint. Then what is fading? Deviation or attenuation that telecommunication signal experiences over certain propagation media, that is fading. It may vary with time, geographical position or radio frequency and is often modeled as random process. In wireless system, fading may either be due to multipath propagation or due to shadowing from obstacles. Reflectors in the environment surrounding a transmitter and receiver create multiple paths that a transmitted signal can traverse. The receiver sees the superposition of multiple copies of the transmitted signal, each traversing a different path. Each signal will experience differences in attenuation, delay and phase shift while traveling from the source to the receiver. This can result in either constructive or destructive interference, amplifying or attenuating the signal power seen at the receiver. Strong destructive interference is frequently referred to as a deep fade and may result in temporary failure of communication due to a severe drop in the channel signal to noise ratio. Here is the diagram which is showing the wireless propagation environment. Here we can see this one is the line of sight path and these are the non-line of sight path. Here we can see that per non-line of sight path we are getting some angle spread. So we can see that with this, when the transmitting signal is transmitted, then there is some local scattering here. Now we will see the types of fading. There are two types of fading. First one is large scale fading and second one is small scale fading. In large scale fading, the signal and the power will attenuate or fluctuate over a large span of time. And in small scale fading, the signal or power will fluctuate or attenuate with a small period of time. Here, in the large scale fading, there are two types. First one is path loss and second one is shadowing. In a small scale fading, there are two types. First one is multipath delay spread and second one is Doppler spread. In multipath delay spread, again there are two types. First one is flat fading, second one is frequency selective fading. In Doppler spread, also there are two types. First one is fast fading and second one is slow fading. Then we have to know that what is the need of diversity. If a fading radio signal is received through only one channel, then in a deep fade the signal could be lost and there is nothing that can be done. If one radio path undergoes a deep fade, another independent path may have a strong signal. Diversity is a way to protect against deep fades, a choice to combat fading. Powerful communication techniques to provide wireless link improvements at relatively low cost, provides two or more input at the receiver such that fading phenomena among these inputs are uncorrelated. Here we can see that this is the modulator and from this the signal are modulated and sent over n number of channels. From n number of channels we are getting n number of signals and that will be passed through the diversity combiner. Then after that, from the diversity combiner we will get our signal, then we have to demodulate our signal, then we will get our output signal. Here we we can see in this graph here the two channels are highly correlated. So we can see that the two signals what we are getting, they are superimposing on each other. And in this graph we are seeing that the two signals are uncorrelated. Here we are using two channels uncorrelated. So we are getting these two signals with different properties. Then the types of diversity. There are two types. One is macroscopic diversity, second one is microscopic diversity. In macroscopic diversity, we can say that it prevents large scale fading. Large scale fading is caused by shadowing due to variation in both the terrain profile and the nature of the surroundings. Large scale fading is log normally distributed signal. This fading is prevented by selecting an antenna which is not shadowed when others are. This allows increase in the SNR ratio. Long-term fading can be mitigated by macroscopic diversity. Apply on separated antenna site like the diversity using two base station. In microscopic diversity, we can say that it can prevent small scale fading. Small scale fading is caused by multiple reflections from the surroundings. It is characterized by deep and rapid amplitude fluctuations which occur as the mobile moves over distances of a few wavelengths. This fading is prevented by selecting an antenna which gives a strong signal that mitigates this small signal fading effects. Short-term fading can be mitigated by the diversity using multiple antennas on the base station or mobile unit. Then types of diversity. There are some types. First one is frequency diversity, time diversity, polarization diversity, and space diversity. Under space diversity, there are again four types: selection diversity, scanning diversity, maximum ratio combining, and equal gain combining. These all four are combining techniques of diversity. What is frequency diversity? In frequency diversity, it transmits the same signal with different frequencies. Frequency separation should be less than the coherence bandwidth. Here we can see that frequency is divided with different frequency slots are divided with different frequency slots. And in time diversity, it transmits the information signal repeatedly at regular intervals. The separation should be greater than coherence time. Then what is polarization diversity? It uses antenna of different polarizations, that is horizontal and vertical. The antennas take advantage of the multiple propagation characteristics to receive separate uncorrelated signals. SNR is improved by up to 12 dB even in line of sight channels. Then what is space diversity? A method of transmission or reception or both in which the effect of fading are minimized by the simultaneous use of two or more physical separated antennas. Here we can see that this is the single input, single output. So we are using here only one transmitter and only one receiver. Here no diversity technique will be used. And here this is single input, multiple output. Here we are using one transmitter and we are using n number of receiver. So we can say that here the receiving diversity is being used. Then third one is multiple input, single output. Here we are using multiple number of transmitter but only one receiver. Here we can say that we are using transmit diversity. And in the multiple input, multiple output, we are using n number of transmitter or n number of receiver. So we can say that transmit and receiving diversity, this is the best one. Then combining techniques. Selection combining, this is the simple and cheap. Receiver select branch with highest instantaneous SNR. We can see in this figure, we can transmit the signal from our transmitter. Then these signals will go through the n number of channels. Then from each channel we will get our signal then that signal will be monitored through SNR value. Then the signal with highest SNR value will be received as a powerful signal. Then feedback or scanning combining. Scan each antenna until a signal is found that is above predetermined threshold. If signal drops below threshold, then we will rescan. Only one receiver is required since only receiving one signal at a time. So this is less costly but still needed. Multiple antennas are used here. Then maximal ratio combining technique. Combining all the signals in a co-phased and weighted manner so as to have the highest achievable SNR at the receiver at all times. Optimal technique to maximize output SNR, a mean of combining the signals from all receiver branches so that signals with a higher received power have a larger influence on the final output. Here we can see that we are transmitting our signals from the transmitter and these signals are passing through n number of channels. Then we are weighted each signals like W1, W2 and W1. Then all these signals will be co-phased and we will receive our output signals. Then equal gain combining. Combining all the signals in a co-phased manner with unity weights for all signal levels so as to have the highest achievable SNR at the receiver. At all times, the phase is adjusted for each received signal so that vectors add in phase. Performance is marginally inferior to maximal ratio combining but superior to selective diversity. Simplified method of maximal ratio combining we can say. The transmitter is transmitting n number of transmitter is transmitting the signal and these signals are passing through the n number of channels. Here also we are co-phasing our signals, but here we are using with unity weights. Then we will combine our signal and with the highest SNR ratio we will get our signal as the output signal. Then here is comparison of different diversity schemes. There are some advantages and disadvantages of each diversity schemes. First one is space diversity. It is easy to design, but hardware size could be large. In polarization diversity, no space is necessary, but only one branch diversity schemes are possible. This is the disadvantage. In frequency diversity, any number of diversity branches are selectable, but L times more power and spectrum are necessary. This is the disadvantage. In time diversity, no space is necessary. Any number of diversity branches are selectable. But the disadvantage is L times more spectrum are necessary. Large buffer memory is necessary with FT is small. Then we will see some of the applications. The major application we can say that the major application is TDS OFDM. In this system, we are using a space-time frequency coding scheme. The performance improvement of this system with the method is theoretically analyzed or computer simulated, showing its superior performance in the presence of both time and frequency selective environment. This scheme reduces the computational load by about 70% in above system. Then, I will like to conclude that the diversity is used to provide the receiver with several replicas of the same signal. As higher as the received signal replicas are decorrelated, as much as the diversity gain. Diversity techniques are used to improve the performance of the ratio channel without increasing in transmitted power. Equal gain combining performs very close to MRC. But among different combining techniques, MRC has the best performance and the highest complexity, and SC has the lowest performance and the least complexity. That's all from my side. Thank you.